Hi, Science 30. So I am going to post first lecture today for electromagnetism. I'm going to give you a little outline about electricity and electric fields and magnetic fields, and hopefully talk about electric field strength and gravitational field strength. In your data booklet, the main equations are on page 2 and page 3 for this unit. You're going to be looking at force of gravity, gravitational field strength, electric field strength, so those three equations here. You've got some constants. I'm going to give you some examples, right? Like big G equals 6.67 times 10 to the negative 11th, Newton meter squared, kilogram squared. You have Coulomb constants for electric field strength. I'm going to use these as the lecture goes on. You also have some data about some masses of celestial objects, like the mass of the Earth, the radius of the Earth, the mass of the Sun, the distance of a light year, acceleration due to gravity, and the gravitational field strength of the Earth. You'll be using those as constants. And electricity formulas, I'm going to be using these with circuits. So power, voltage, energy, different transformer equations when we convert voltage, resistance in parallel and series circuits. A lot of you guys have seen these equations before. Wave formulas is for the second half of this unit. When we talk about the electromagnetic spectrum, you have the electromagnetic spectrum here as well, with different waves that have different wavelengths and frequencies. Those are going to be the main things you're going to need to know for this unit. I'm going to do a couple of examples, mathematical examples on the board. The first thing we need to understand is electric field strength. So looking at a lightning storm is a good example. When we look at thunder and lightning, electromagnetism starts on page 312. But if I pop to slide 6 here, when we look at electric field lines, you should be able to recognize what happens here. So an electric field is an area where electricity is exhibiting a force in a given region. So an electric field is a property of the space around a source charge. So something that's negatively charged and something that's positively charged. Any charged object has an electric field. So you do have positive and negative charges. Unlike charges attract and like charges repel. Electric field strength lines always go from a positive test body to a negative test body, and you can see this. So in an electric field, you'll have a positive terminal and you'll have a negative terminal, and the field strength lines always go from positive to negative because electrons flow away from the positive test source. So the positive test source has a deficit of negative charge, and the negative test body is where the electrons gather, and that's why it's negative. Okay, so we can detect electric fields by using test bodies, which is anything that experiences a force due to the presence of a field. Now remember, when you look at positive and negative charges, protons are positively charged in the nucleus. Neutrons don't have a charge, and electrons don't exist inside the nucleus. They exist in quantized orbital probabilities outside the actual nucleus itself, and as a result, electrons can move. Okay, so negative test charge can move. Positive test charge doesn't. Okay, so when you look at electric fields, the strength of the field is proportional to the distance from the test bodies. So the closer you are to a test body, the stronger the field, obviously. But electric field lines always go from negative to positive. So you should understand that. So if I have two like charges repelling, okay, the field lines will actually repel away from each other. Okay, so they won't be attracted to each other, but the field lines will point away from the positive charge. If we have two test bodies in a field that are negative, then the lines actually go towards the negative test body. So electric field lines always go towards a negative test source. Right, so this could be an electrical appliance, this could be, celestial objects, right, big electromagnetic fields with stars and planets and things like that. Electricity can move mass and can move objects. Right, you see that with any electrical appliance. So they use these field lines in order to do that, and the electrons move along the field lines, and then that causes electricity to do work. So I'll give you the example of what happens in a thunderstorm. I just got to change my colors here because we're going to use the ground and we're going to use the atmosphere above. So you guys all know how static electricity works, right? You rub two electrostatic objects together, and then that creates force, right? Usually you see it as a shock, or like your hair sticking up. But what that's doing is separating charge and creating field lines. And when we have a big thunderstorm, you get large clouds and they rub up against each other, and that causes static electricity. Okay, so that causes static electricity, and then these two air masses that are combining with each other, they swirl and cause a big building cloud called a cumulonimbus cloud. And then what happens is this big amount of friction separates charge. So here's the ground. So remember that positive charge can't move. So you have, right, so the clouds are largely made up of water, and there's hydrogen and oxygen and, other types of trace elements in there. But they're protons, right? The positive charges are protons and they can't move. So what happens is the protons stay stationary, and you get this net buildup of positive charge. Remember, the ground's made of matter as well. Okay, and then let's say we have a little hill here. Maybe there's a tree on it. Okay, so the ground's also made of matter, and matter is composed of protons and neutrons and electrons, and the protons can't move because they're stuck in the nucleus of atoms. But electrons exist in orbits, so they can move. So what happens is, in the ground, electrons, negatively charged electrons, they actually move to the surface because during a big thunder and lightning storm. So this rubbing of the clouds separates the charge. Negative charge is repelled by the negative charge in the earth, and then the negative electrons are attracted to the positive protons of a cloud as this friction happens. Okay, and then you get field lines that are being created, right? So, so remember that the field lines always go towards negative test bodies. So if there's buildup of electrons in the ground, and that actually creates electric field lines. So there's this buildup of charge, and then what happens is these electrons build up in the ground, and then eventually this charge builds up so extreme in the surface that it has to be dissipated, and that's what creates lightning. So eventually there's so much electrons built up in the ground that they can actually move along the field lines, and the lightning actually moves toward the cloud. So lightning actually starts from the ground up. It does not start from the cloud down. Right? So you see the lightning first because it travels at the speed of light, and then you hear the thunder after. And the thunder is the sound energy that's created from the lightning dissipated. So lightning actually goes from the ground up, which most of us don't know. So if I'm an individual that is trying to get away from lightning in a thunderstorm, like being under a tree is not a good idea, right? I want to be in a low-lying area because you'll follow, so where you either sit in your car because your tires are an insulator of electricity because it can't travel through rubber, or you get to a low-lying area and lie flat because the lightning is going to go from the least distance possible. So lightning actually might move up through a large tree. That's what causes a lot of natural forest fires. Right? Most of our forest fires around here are caused by idiots throwing smokes into a forest. But natural forest fires are caused by lightning dissipating and that negative charge moving from the ground up to the clouds. So these are electric field lines that you see naturally in the charge separation. Okay. So you should understand how electric fields work. The field lines always go from positive to negative. You'll have attracting and repelling charges. You're also going to have different strengths of electric fields. Just a sec here. And the strength of the electric field is determined by the density of the lines. So if you have more lines, that means that there's more electrons present. And electrons are quantified as a value called a coulomb. So they're measured as C. So if there's more coulombs of electrons present, you have a higher voltage object. Okay, so this would be the least dense electric field. This would be in the middle, and that would be the strongest electric field. Okay. So again, the direction of an electric field line is always determined by the direction of the force on a positive test body. A positive test charge leaves a positive source and moves toward the negative source. So electric field lines always point away from a positive test source and go towards a negative test source. That's exactly what I did here. Okay, so the field lines, and you can see that build up. And the charge separation with the electric field lines. And these electric field lines are actually the lightning dissipating. I'm not going to talk about magnetism right now. Okay, so when we look at units of electrons, a coulomb is actually 6.25 times 10 to the 18th electrons. So 1 coulomb is that many electrons. So you can use that as a conversion factor. So 1C equals 6.25 times 10 to the 18th E negatives. I'll do a couple of questions related to that in a second. You can also quantify the amount of coulombs, and that's the charge. So an electron charge is measured as Q, and again, it's the amount of coulombs that are present or moving through an electrical object. And that determines the energy, right? So, so this is an equation that you need to know. So energy, which is measured in joules, is a function of voltage times charge. So voltage is, and you guys have all seen this term before, potential difference. So it's the difference in the amount of electrons between two test sources. So as units of charge move from one object to another, they gain potential energy. And the charge moving from one object to another is called voltage. So if there's a larger difference in electrons between a source and a receiver of electrons, you get a higher voltage. Okay, so it's the difference in electrons. So voltage equals E over C, or energy equals voltage times charge. So the amount of electrons and the difference in the amount of electrons between two objects gives us energy. So when we look at charge and we look at energy, right, so voltage indicates the joules of energy transferred. There's two things that indicate level of voltage. So if there's more coulombs present and there's a larger difference in coulombs between two source objects, then you get a larger voltage. So something that is high voltage has a lot of coulombs. So for example, right, if we have like an electrical transformer box that is 50,000 volts, that means that in comparison to the average human body, there's 50,000 more volts of electricity than is present in the human body. So if I were to touch that electrical object, it could transfer 50,000 volts of electricity to my body. All right. So right now, if our body, let's say for example, we run on like a voltage of, I don't know, like 0.3 volts or something like that when we make electricity in our body from the movement of ions. So 50,000 versus 0.3 volts is a massive amount. But let's say my body ran on like 46,000 volts. Well, there'd only be about 4,000 volts of transfer between a 50,000 volt object in my body. So it wouldn't necessarily be considered high voltage anymore, right? So it's not only just the amount of coulombs of electrons that are present, but it's also the difference between two objects. So voltage is perceptual as well, right? Okay, so I'm going to do a couple questions here. So this is page 316. Question number 4. And it says, a lightning strike transferred about 15 coulombs of charge from a cloud to a building. The voltage between the cloud and the building was 1.5 times 10 to the 8th volts. Calculate the energy delivered in the lightning strike. Okay, so remember, energy is measured in joules. And energy in this circumstance is a function of Q times V. Okay? Right, so a volt is a joule per coulomb. And Q is coulomb, so we can cancel the C out and get an answer in joules. Okay, so we have my Q value is 15 coulombs and my voltage is 1.5 times 10 to the 8th volts, joule per coulomb. So I can cancel those coulombs out, and that's going to be 15 times 1.5 times 10 to the 8th. Shoot. Calculator doesn't seem to be working right now.